Good morning, everybody. Welcome to another exciting morning at Chem 1105 with your host, me, Dr. White. Hi, everybody. And let me remind you, after class today, by noon at the latest, maybe give or take a couple of minutes, I will send out an individual email to each of you with the password for test number 1. And it says this, and you'll have until tomorrow, 1 p.m. to finish test number 1 and upload your answers as a single PDF file to the assignment area Blackboard. And I'll show you that in a second, maybe more than 1 second. And it should take you about 40 minutes, but if you need 2 hours, if you need a little more, that's okay. That's the advantage of taking an online course with me. But let's go to Student View. Now, click on Assignments. You'll see, oh, look, test number 1. And when you click on this, you're going to have to, that's the PDF file, test number 1, to download it, you will have to put in a password, which I will send you. This test and all my tests, all passwords are lowercase. That makes mistakes. Anybody having a mistake, less likely putting in the password. And by tomorrow, you'll click on this again. And if I click on this, when you download it here, you'll need a password. To submit it, you click on Browse Local Files, and it'll ask you which one. You'll pick it, open it, click Submit. Now, the way I have my tests and labs too, you can make more than 1 submission. So for some reason, oh, I put the wrong file, or I put the empty one in, not the one with my answers, you can go back and do it again. Am I nice or what? Don't say anything. Don't tell anybody. So I'll be sending that out to you. Once you take the test, if you forgot, hold on, I got to reboot. I'm rebooted. If you forgot, in my class, in my world, there's no such thing as a dumb question. That's including about tests. Now, since we're not face-to-face, you can't come up to me with your question. If I were teaching face-to-face, students do that, and I allow that. Why not? They're not clear about something, I clarify things. Therefore, if you have a question while you're taking the test, email me the question or come tonight to my office hours from 6 to 7:15. Now, I have to teach this afternoon online at another school. So starting about 4:30, every 2 hours until maybe 9 o'clock, I will be checking my email. And tomorrow morning until I go to my dentist. But anyways, well, he's a great dentist. There are better things in life I'd rather do. But he's still not nice, really, really great dentist. I will check from the morning till 9 a.m. And when I get back, I'll check. I don't know when. I think it's an hour and a half appointment. But yep. All right. Now, another thing I'd like to address right now is emails. I have 4 email accounts. Yep, 4. I teach at 2 schools, so each school gives me an email account. I have my personal email account, and I have a consulting business, and that's a separate email from my personal. I get anywhere from 10 to 50 or 60 emails a day. Yep. If once in a while it happens, and I apologize, 1 or more of your emails will get slipped through the crack, and I don't answer it. send me another one. Eventually, oh, I forgot to do that. Now, when it comes to emails, because of my teaching schedule, I check it twice a day. Once in the morning by 7:30, quarter to 8 at the latest. After that, I will not, because I can't, because I'm busy, check my email until about 5 or 6 or 7 o'clock later in the afternoon or evening. So if you send me a bunch of emails, 9, 10, 11 o'clock in the morning, I'm not going to get to them. I'm teaching here. So I just wanted to remind you that. Any questions? Anything you'd like me to go over once again before I move on? Looking at the chat. All right, let's move on. Now, we were talking about Lewis structures for molecules. We did these. Let's do another one. Oh, what would be a good one? Oh, I've got a good one. And the question would be, and the question is, draw the Lewis structure for hydrogen sulfide. Now, hydrogen sulfide, I haven't been to a forest preserve in a long time, but when I was young and my parents would take me to a couple summers when I was real young, summer camp. Remember the hand pumps for the water in the long ago in the forest reserves? I don't know, they have them. And you go drink the water. Oh, it smells like a rotten egg. Oh, is that stinky? Well, what you were smelling was this, hydrogen sulfide. Now, how do you draw the Lewis structure for hydrogen sulfide? You need to find how many valence electrons hydrogen sulfur has. Oh, I forgot to open up something. And this is a periodic table, by the way. You will be able to, if you look at test 1 in the assignment area, this is one of the files you should download, this one, because this is the periodic table you should use for today's test. But anyways, hydrogen, we talk about Lewis structures. You look at the top, not the atomic number, but the number on top for how many valence electrons. Hydrogen H1, sulfur S right over here, atomic number 16. You look on the top, has 6 valence electrons. And you need that to do the problem. So we have 1 valence electron for hydrogen. I put the 1 there because if I don't put the extra lines, which I normally don't, it looks like the word hive. Boy, I wonder if the hydrogen will come out and sting you. Oh, is that bad? I'm sorry. And sulfur has 6 valence electrons. Well, the only way this is going to work is with sulfur in the middle. So I'll put my 1 there. Remember, you do for elements, you have 1 dot on each side, and then you'll double up. Now, this is the way organic chemists do sulfur, and I'm an organic chemist. You can do it different ways. And remember, there are two hydrogens. Now, this hydrogen says to this sulfur, oh, look, I've got an unpaired valence electron. You do, let's share. And they do. This hydrogen says, I've got an unshared pair electron, valence electron. You've got one, let's share. And they do. And now you have the structure, Lewis structure for hydrogen sulfide. Stinky, real stinky. Now, let's go through and check the octet rule. Remember, in molecules, especially Lewis structures, the way I have it, and I'll show you something else later today, atoms share, gain, or lose electrons in order to have an octet. The one exception hydrogen octet is 2, not 8. So let's look at this hydrogen. How many valence electrons does it have alone and is sharing? And the answer is 2. Count the dots right here. 1, 2. And we go to the other hydrogen. How many valence electrons does it have alone or sharing? And the answer is 2. So each hydrogen has its octet. Remember, hydrogen octet is really 2, not 8. But let's look at sulfur. And sulfur should have an octet, 8 valence electrons, shared and unshared. I like my special effects. And if we look at that, in that blue circle, how many pairs of dots do we see? 2, 4, 6, 8. Octet. And that's how you know this is correct. Now, you learned yesterday that there are 3 types of covalent bonds. Almost hand wrote it out in cursive until I remembered you people, most of you can't read cursive. Oi. Actually, that's an oy vey. You don't know what oy vey means? Look it up. Remember, what I'm going through now will be on test 2, not test 1. So you have a single bond, which is 1 pair of electrons being shared between 2 atoms. You have a double bond, 2 pair of electrons being shared between 2 atoms. And you have a triple bond, 3 pair of electrons being shared between atoms. Let me rewrite the Lewis structure of hydrogen sulfide. What type of bond, or I should say, what type of bonds, covalent bonds, are in hydrogen sulfide? You know, the stinky stuff. Oh boy, it is stinky. Time's up. There's 1 pair of electron being shared there. That's a single bond. And right here, there's one pair of electrons being shared. Same thing over here. I'll make them bigger so you can see it. And those are a single bond. So there are two single bonds in hydrogen sulfide, just like in water, which we did yesterday. Now, something I skipped yesterday, and I can go back to right now, because I can, is the following: polyatomic ions. Now, you learned earlier, and again, this is for test 2 material, an ion with polyatomic ions are atoms held together more than 2. And they're ion. They have a positive or negative charge. And it's an ion now I'm going to teach you with covalent bonds between atoms of a polyatomic ion. What does that mean? Well, let's do the Lewis structure for this compound, NaOH. This is sodium hydroxide. If you remember, I taught you this is lye. It's a very important base used in the United States and elsewhere. And it has one sodium, one oxygen, one hydrogen. Well, to do the Lewis structure, draw the Lewis structure, you need to know valence electrons. So let's go to our friendly neighborhood periodic table. And if we look for hydrogen, look at the top, we're in red, it has one valence electron. If we look down below, sodium, Na, also has one valence electron. So we got our H, we got our sodium, Na, we need our oxygen. Don't look at the atomic number. That's the number of electrons and protons. You look at the number on top in red, and that is 6. So oxygen has 6 valence electrons. By the way, I use these so often I know them by heart, but you don't. So sodium has 1 valence electron. Oxygen has 6 valence electrons. And hydrogen has 1 valence electron. Now, I'm going to write it out and I'm going to show it to you. Don't you like how I can be very subtle? Hint, know this. And what should you know? Here's something, let me rewrite it a better way. And you should know all alkali metal elements, all alkaline earth metal elements only form ionic bonds. You will never find an alkali metal or an alkaline earth metal in a covalent bond. You won't. By the way, if you do, let me know, and we'll be rich beyond my wildest dreams. And that goes beyond having my own island in the South Pacific, my own Lamborghini and Ferrari. Yes, I've been in them, but I've never owned one. And my own fleet of fighter jets for me to play with. It goes beyond that. It doesn't exist. So what does that mean? Well, if we look at sodium, you learn how to figure what ion sodium forms. I went through this more than once, so I'll do it. Sodium forms a +1 cation. Now, we still have the oxygen and hydrogen to go. So I'll do my valence electrons for oxygen, 6 of them. Each dot is a pair of each dot is a valence electron. Put one on each side until you pair up. Hydrogen has 1. And the hydrogen says to the oxygen, hey, how about you've got a unpaired valence electron? I do, let's share. And it does. And now we look at this and we say, oh, we're done. Let's check. Hydrogen has 2 valence electrons being shared right here. Oh, that's good. Now, I'm going to remove that circle. Well, a better way is an eraser. And if we look at oxygen, it's got oh no, it doesn't have an octet. That's 2, 4, 6, 7. What do we do? Well, let's take a look again. Now, sodium had 1 valence electron, but when it's in a cation like this, it gave it up. And where did it go? It went to the oxygen right there. This right here, to get to here, you lose that. Well, it doesn't just go floating off in the air. Oh, there's a valence electron. I got one. Look. No. Oh, it's really bad humor. It goes over to the oxygen. Now oxygen has an octet, but it has an extra electron. And because it has an extra electron, and I'm putting it brackets so you can tell, it has a minus charge. So let's look at sodium hydroxide. You have the hydroxide polyatomic ion, which has a negative charge. But between the oxygen and the hydrogen, there's a covalent bond. But between the sodium plus and the hydroxide, the whole ion, there's a ionic bond. So in sodium hydroxide, there are 2 types of bond. One is an ionic bond. The other type is a covalent single bond. And that's how you do it. Let me go through this again. Draw the Lewis structure for sodium hydroxide. We look at how many valence electrons. Sodium has 1, oxygen has 6, hydrogen has 1. And I should do this. All right. Now, hint, know this. All alkali metals and alkaline earth metals only form ionic bonds. That means they either give up or accept protons. So here we have sodium hydroxide. And the sodium will form a cation. And I taught you how to figure out that's Na+. But oxygen has 6 valence electrons, hydrogen 1, they share a pair, but you have 1 missing electron to get the octet for oxygen. And where does it get that? It gets this. Oh, I don't like that color. That's why I don't use it. Can't see anything. It gets that extra electron because this gets transferred over to here to form this. And that's how you do an ionic bond. Let's do one more. And this is potassium cyanide. That and sodium cyanide are dangerous chemicals, they're poisons. But let's look at this. How do you draw it? Well, first of all, you need the number of valence electrons for potassium, carbon, and nitrogen. And how do you find that out? You go to your friendly neighborhood periodic table. And here we have it. And we need potassium, K, and that has 1 valence electron. We need carbon, C, look at top, it has 4 valence electrons. I gotta get this fixed. Uh-oh. Uh-oh, my hands, oh, never mind. I said it's bad humor. Wednesday, 4 valence electrons. And nitrogen, N, has 5 valence electrons. So let's go back. So potassium, 1 valence electron, carbon, 4 valence electrons, nitrogen, 5. Now, potassium, ooh, let's look at something. Potassium right here is an alkali metal. And you know alkali metals and alkaline earth metals, first and second column, always form an ion. And just like sodium, potassium forms a +1 ion. So I know this can't be in a covalent bond because it forms this ion. Now, carbon and nitrogen can. So I have this potassium, I have carbon with 4 valence electrons, nitrogen with 5 valence electrons. And carbon looks at the nitrogen and says, oh, look, you have 1, 2, 3 unpaired valence electron. Carbon says, oh, I have 1, 2, 3 unpaired valence electrons. Let's share. And they do. 1, 2, 3. Here's your nitrogens, 1, 2, 3. When those are left over, don't forget the non-bonding electrons are still there. Now there's this one that's not being used, and you have the potassium. Now, if we look at nitrogen, shared and non-shared, I should say bonded, non-bonded electrons, count the dots, 2, 4, 6, 8. That adds up to 8 octet. Now, if we do the same thing for carbon, we have 2, 4, 6, 7. That's not 8. That's not finished. Something's got to go on. And remember, to get to this, potassium gave up 1 valence electron. And no, it's not floating in the air. Oh, I got it. Nope. It was transferred over to the carbon. And here it is. And now this has an extra electron, which means it's got a minus charge. So you have a potassium with a plus charge. Let me clean this up. And the cyanide anion so polyatomic anion has a negative charge. And between the cyanide anion and the potassium cation, there's an ionic bond. If we look at carbon now, how many shared and bonded, non-bonding valence electrons does it have? 2, 4, 6, 8. Yay! It has its octet. Now, what kind of covalent bond exists in the cyanide anion? Your turn. And before you answer that, oh, look, someone wrote a nice table on the screen there. Single bond, 1 pair of electrons. Double bond, 2 pair. Triple bond, 3 pair. I think this hand does it better. It does. So, what kind of chemical covalent bond exists between carbon and nitrogen in the cyanide anion? And the answer is this right here is a triple bond. So this molecule has 2 types of chemical bonds. Between the potassium cation and the cyanide anion, there is a ionic bond. Between the carbon and nitrogen in the cyanide anion, there's a triple bond. And that's how you do polyatomic ions. Now we went through single bond, 1 pair of electrons being shared, double bond, 2 pairs, and you should know this for test 2. Hint, double hint, triple hint, and double bond, 2 pair of electrons being shared between 2 atoms, and a triple bond, 3 pairs of electrons being shared between 2 atoms. Now we did the Lewis structure for these, so let's move on. Now, it turns out molecules and ions have shapes. And they exist in 3 dimensions, just like you and I. And the shapes of molecules are very important in understanding how molecules interact, like in your body, like your RNA, your DNA, like your hormones, which are all chemicals. Yep, they are. You don't think about it. I bet you don't even think about it. Everybody, touch the back of your hand. Hopefully it won't hurt. Go ahead, do that. Or if you got some hair, like I still have some, touch it. Those are molecules held together to form your skin. Has atoms, I hope I'm not scaring anybody, to make your skin. And notice how I have wavy hair, what's left of it. Boy. Anyways, it's better than my best friend. He's like, he always says, I wish I had as much hair as you do. And I said, well, back here I'm bald. He said, but you still have some on top. Shh, don't tell him I said that. But anyways, atoms and molecules are shaped in such a way and how they interact are causing this to be curly or wavy. It does. So how do we know? How does an atom form a certain shape? And that's governed by the VSEPR theory. Now, the previous slide, the next couple of slides, click. I'm turning the switch. Will this be on a test? No. But it's still important for you to know, like for other classes. And VSEPR stands for valence electron pair repulsion theory. And this is a theory that shapes of molecules are based on minimizing repulsions of electrons in an atom of a molecule. Guess what electrons those are? Yep, the valence electrons. Now, if we look at Wikipedia, I used to say Wikipedia in my class, would always yell at me a couple of years. No, it's Wikipedia. And they finally taught me how to pronounce it right. Now, if we look at, let me go back to my slides since I think I have it. Now, the molecular geometry from VSEPR is based on a number of electron pairs, bonds to an atom. And those are the bonded and non-bonded valence electrons. Now, based on this, and again, switches off, click. Key molecules have their geometry. Now, CH4 is methane. You know that as natural gas. And it has a shape of tetrahedral. I'll show you that in a second. Ammonia has a shape called trigonal pyramidal. Say that 5 times fast. No, I won't. And, oh, remember the non-bonding pair of electrons on nitrogen. And water is bent. What do I mean by all this? Well, if you scroll down, you can see we're here and number 4. If you think of X as hydrogen, each line is a pair of electrons, and the center for A, that is the carbon. And this is tetrahedral. Hold on one second, maybe 2. Look out, it's Dr. White's show and tell. Now, in organic chemistry, we use models to build things. And this is a carbon in the center. And each line at the end, we don't show it, but there's a hydrogen. And this would be methane. And this overall shape is called tetrahedral. Tetra, 4 sides, hedron as polygon, polysided compound or shape. And methane exists like that. Now, I'll teach you later that you can have different shapes. Now, if this were water, the 2 silver would be the non-bonding electrons. And therefore, all that really exists are hydrogen, hydrogen. Let me hold it up like this, and the oxygen in the center. Forget about the metal tubes. And it's bent. Again, switch is off, but Dr. White's having fun. If we look over here, where it has molecular geometry, 2 lone pairs, that's what the E is, it's bent. A is oxygen, X is hydrogen. Now, if we look at the same one, where it says 1 lone pair, non-bonding electrons, if this were nitrogen, hydrogen here, 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 this is called trigonal pyramidal. And you forget about the E, and it looks like a pyramid. I wonder where they got the name. And trigonal means 3 hydrogen. So molecules have shapes. This and some other forces affect the shapes of things in your body, like your RNA and DNA. Yep. Now, let's talk about another thing. And I'm going to be talking about this throughout the semester, but I'm not going to ask on a test what it is. But other courses, you may need to know this. Now, let's talk about electronegativity and bond polarity. Again, click, will this be on a test? No, but you really should know it. And what is electronegativity? That's the ability of an atom to attract electrons to itself. Now, think of 2 people, one strong and big and one not. And what if they were sharing an umbrella and they're raining outside? Well, they're sharing the umbrella, but the bigger person is holding the umbrella more over him or her than the other person. It's covering some of that person, but the other person is still getting wet. And that's what electronegativity is, except instead of an umbrella, it's electrons. Oh, by the way, don't tell my older sister, I told the story about her keeping the umbrella over her more than me. She was 14, I was 7, much bigger than me. I didn't have a chance. Don't tell anybody I sold that. But anyways, when we talk about electronegativity, the electronegativity of an element increases as you move from right to left on the periodic table and as you move from the bottom to the top. What does that mean? Well, let's look at a periodic table. And here we have a periodic table. Let's look at hydrogen. And as we go across to, say, oxygen, this way, it's more electronegative, going this way from left to right, from, say, lithium to fluorine, it becomes more electronegative. The element, that means it's stronger to be able to hold on or share in electrons in a covalent bond. So if we look at hydrogen and oxygen, Since oxygen is this way, it's more electronegative as hydrogen. Now, if you look at fluorine, chlorine, bromine, and iodine, as you go up the periodic table, it's more electronegative. And fluorine is the most electronegative element on the periodic table. So what does that mean? Oh, good question. Thank you. You're welcome. There are different types of covalent bonds, again, switches off. Non-polar covalent bond, atoms with similar or identical electronegativity. So there's equal sharing of electrons. Methane, turns out hydrogen and carbon excuse me, electronegativities are similar. So the sharing of the two electrons between, say, this hydrogen and this carbon are same. They're sharing equally. Let's look at, chemical near and dear to our heart, water. Bet you didn't think water is a chemical. Now, I'm going to draw it like its shape. And you can do it straight too. Now here, hydrogen has a lower electronegativity than oxygen. Let me get to the next slide. And we're going to create a polar covalent bond. And that's a covalent bond between different atoms with different electronegativities. Now, this is sometimes called a dipole. That's a polar bond, again, switches off, click, that has separation of charges, positive and negative. The charge separation is only partial. And I'll explain more of this as we move on. It's not really an ionic bond, since there's some sharing of the electron pairs of the covalent bond. Since it's only a small separation, small, not big, we use the Greek lowercase delta and the uppercase and the charge symbol plus or minus next to the delta to show that. So I have water. Now, I'm going to do it this way, not show the valence electrons. What this means is this bond, the electrons in a line now, don't use a line on my class. Well, you can. But anyways, shows there's a covalent bond. But because the oxygen is more electronegative, there's a slight negative charge on the oxygen and a slight positive charge on the hydrogen. Same thing on this side. And this really is happening in water. If I can spell it, hold on. Dr. White just had a typical brain freeze. I was going to write H2O as I was spelling it. Oh no. It's time for a break. Let's take about a 5-minute break. I can get up and stretch, and we'll continue after the break. I'll see you then. I'm back. Profound. As you couldn't figure that out. All right, we're talking about how you can have dipole moments. Di in chemistry means two, and pole, polarity. And there's a dipole in water. Now, sometimes the dipoles cancel each other out, sometimes they don't. Uh-oh, we're almost done with this chapter. Now, there's one slide I don't have, so I'm going to do it the old-fashioned way. Write it on the whiteboard. Switch is on. If it were a dial that goes to 10, I've just turned it to 50. I stole that from the movie. This is Spinal Tap. But hey, know this. I'll write it this way. Now, as you learned earlier, water, because the difference in electronegativities between hydrogen, which is all the way over here on the periodic table, and oxygen, which is all the way over here, more electronegative, don't equally share the line, which is a pair of electrons, valence electrons, between each other. And oxygen says, I'm bigger than you, just like my sister did with the umbrella. Let's hold the electrons a little closer to me. So it has a slight, remember this means slight or little negative charge. The oxygen has a slight positive charge. Now, if we go over this molecule, guess what? Same thing on that water molecule. Now, it turns out opposites attract. Now, here we have a slight positive charge on this oxygen. We have a slight negative charge, and there's a slight attraction. This is not a full ionic bond, but it is a force between the two. That's what those dotted lines are. And this, even though it's not a true chemical bond, is a very important force that's been given a special name. And that's a hydrogen bond. And I'll teach you more about hydrogen bonds later on, but, well, I can tell you now, but I'll teach it again on a slide later on when we get into solutions. But when you have either oxygen, nitrogen, or fluorine with a hydrogen on it, which water does, you have that dipole moment, separation, slight separation, a charge, and between opposite charges, there's a very tiny charge, but it's important. How important? See the stuff in this bottle? Water. No, it's not vodka. But anyways, it's water. And it's a liquid at room temperature. My room. What's my room temperature right now? Ooh, I keep it warm in my house when I'm teaching, 74 degrees Fahrenheit. That's the room temperature. Theoretically, 75 is room temperature. But at room temperature, water is a liquid. If you look at molecules with similar molecular weight, which I'll teach you about, other molecules with the same weight, which should have the same melting and boiling point as water, are all gas. Why isn't water a gas? It should be. at this temperature. It's not, it's a liquid. Hold on, I'm gonna have some. Yep, it's a liquid because of the hydrogen bonding. If you had X-ray vision, I don't, I wish that'd be interesting. You could see each water molecule, there's that tiny force between them holding them together. And that's what's forming this liquid. And it's one of the important things in our world, because if we didn't have that hydrogen bonding, because of the difference in electronegativity between the oxygen and hydrogen, water right now would be a gas. And think about it, our planet, if water would be a gas, we wouldn't have any oceans. We wouldn't have evolved into life the way we know it. Not to get personal, but I don't know if you can see it well. The blood in my veins wouldn't be a liquid. It's mostly water. If it were not for hydrogen bonding, it would be a gas and we exist totally differently. How? I don't know, but read some science fiction stuff maybe. But anyways, hydrogen bonding, because of the difference in electronegativity of water, makes it a liquid at room temperature. I think I'm about to sneeze. Nope, I stifled it. All right, and this you should know. And ammonia will hydrogen bond too. Well, if we look at this, oh no, we finished chapter 4. What does that mean? It means next Tuesday, I will do chapter 4 practice problems here in the lecture lab after we do the lab next Tuesday. So I would highly recommend, I know yesterday you're doing it tomorrow, test number 1, but you got to keep up. Listen carefully. And it's not meant to scare you, but it is. Test number 1 always has the highest average. It's the easiest test in the semester. Test number 2, historically, when I've taught Chem 1105, not always, but most of the time, has the lowest test average of the semester. It's the hardest test. Relax. I've had a couple classes of 1105 where their test 2 was very high, almost the highest average. Those are great classes. I hope you're a great class. What I'm trying to tell you is you have to keep up. You can't fall behind. So next Tuesday, I'm going to do the chapter 4 problem set. And that means make sure you do it before I do, so you can see how to do it correctly. All right. Guess what time it is? It's new chapter time. And what's that new chapter? I don't know. I have to open it up first. Hold on. Let me close this. And that's chapter 5. And let me show it to you. Now, before I do this, the way the book's written, you can see I don't like it. I didn't like the way the author did some things, how it's ordered. So we're going to do part chapter 5 now, and later in the semester, we will do the second part of chapter 5. So let's look at that. And chapter 5 in your book has the title Chemical Accounting, which it sort of is, but it's a lot more than that. I should tell you, my mother was an accountant, which meant when I started using a checkbook, she'd ask me, did you make sure it balances out? I said, well, I was about a penny or 2 off. And she said, no, you got to go back and check and find why you're 1 or 2 pennies. And I would tell her, why should I spend 20, 30 minutes of my time for 1 or 2 pennies? If I were dollars off a lot, I'd spend the time. being an accountant, she didn't like that. By the way, my older sister was too. I wonder why she became an accountant. I guess my mother. I became a chemist because my father liked chemistry. Yep. All right. Let's talk about a chemical change. I'll never ask on a test, but I'll use this terminology. And guess what? I just did something I didn't want to do. Now, let's make sure. All right, same thing, but I have opened up the PDF file, which I can't write on here when I'm using PDF. All right, let's talk about a chemical change. That's when an original substance is converted to a new substance that has different composition, different way the atoms are put together, and new chemical and physical properties. So whenever you have a chemical change, you start with something, a substance, and you convert it to something new that has different composition, different amount or types of atoms, and new chemical and physical properties. I'll never ask on a test or my final, what's a chemical change? But I'll use terminology. Now, changes during a chemical reaction, the original substance changes to a new substance with different physical properties. Now, this will go over a lab, but I will not ask this on a test, so switch is still off. In inorganic chemistry, or for this class, how do you know there's been a chemical reaction? Well, for this class, there's a change in color. And we'll be doing, I think, a lab with this. Yeah, we will. It's fun. And what does that mean? Well, if you start out pink and it turns blue when you mix two things together to make a chemical reaction for a chemical change, you see that by a change of color. Another way evidence for a chemical reaction is formation of gas. What do we mean by that? Well, if you mix two things together and all of a sudden you see bubbles, you know there's a chemical change. Oh, hold on. Let's see if I can find something. Time to have some fun.
Research shows nostalgia can help you remember ads.
Sorry about the commercial. No, I don't pay extra money. Oh, no, another one. Skip that. Here we have vinegar. Here we have baking soda. Both are chemicals. Here we have a little tray with a container in it. You can do this in your sink too. They pour in some vinegar. By the way, vinegar is water and acetic acid, a homogeneous solution. And now we'll put in the baking powder, soda powder. Watch what happens. See all that bubbles? That's what that foam is, bubbles. Oh, is that cool? Now you know I'm a chemist. Actually, that was the first reaction my father ever taught me when I was about 5. See all the bubbles form? Oh, that was fun. I hope you enjoyed it. I did. And so when you mix two things together and you get what we call a chemical reaction, which you have a chemical change occurring, how do you know? You have bubbles form, gas form. And therefore, That's a chemical reaction. The other thing, when you mix two things together and you form a solid, how do you know that? You see a precipitate. A liquid is two liquids. If you were to pour it together, you'd think, oh, that should be liquid. Well, if those chemicals are both liquid, when you pour them together, you see a solid. Now, we call that in chemistry a precipitate. So, when you mix two things together and you form a new solid, so if it's in solution, a liquid, we call that a precipitate. I thought I could find one. Sorry about the ads. No. All right, everybody see the little glitter falling on your screen right now? A chemist would call that, oh, look, there's a precipitate. Again, the little solids forming and floating to the bottom, we call that a precipitate. Now, this was already in there as a solid, so you weren't forming anything. So there's no chemical reaction in there. But when you form a solid in a chemical reaction, when you mix two things together, you have a chemical reaction. And the last one, when there's a change in temperature, either it gets cold, or it gets hot, there's been a chemical reaction. And if you ever have started a fire in your fireplace, you take wood, you light it on fire, and the wood is reacting with the oxygen in the air. It's called combustion. And guess what? There's a chemical reaction, because don't put your hands too close, but it gets hot. Now, if you've ever seen a match and you strike it to light it, and then you see the paper burn, turns out to light a match to get a flame, there are actually three chemical reactions going on step by step to make the heat change in temperature to make the flame. Now, another one, nope, not my water bottle. Hydrogen bonding. But anyways, if you've ever seen those packs where you crack it, there's a tube inside a pack and you shake it up and the pack gets super cold. So if you don't have ice and you got a sprain or something, you need to put cold heat, cool it down. They're called ice packs. There's no ice in there. That's water and ammonium chloride. You break it, and that's releasing ammonium chloride into the water, and it gets very cold. That's a chemical reaction. So, evidence for a chemical reaction, that means a change in a substance, change in color, formation of gas, bubbles, formation of a solid. We call that, if it's in a liquid, I like my special effects, precipitate, and change in temperature. Now, how do we show chemical reactions. By the way, click not the definition, but you should understand what is a chemical equation. And a chemical equation is a statement, written statement that uses symbols, chemical symbols, and other things too, and formulas instead of words to describe the changes that occur in a chemical reaction. So a chemical equation will show you a chemical reaction. Now, before I go through there's some conventions. Let's go through this. I will never ask you to write this out, but this is important. When you do I better do something first. Let's get a very simple chemical equation for a reaction. Let's say we have some compound A, oops, and we react it with another compound. I'll just call B. How do we show that? A plus B. And then you have an arrow. Oh, I'm doing good arrow day. And let's say you make a compound from reacting A and B, we'll call C. Could have made C and D too. Now, this is what you should know. At the base of the arrow, these are called the reactants. A and B are reactants at the base of the arrow. Now, since Dr. White, me, has worked many decades in the chemical industry, we also call them starting materials, if I can spell it right. And a lot of times I'll say that. So at the base of the arrow, A and B are the reactants. What are you reacting together to do a chemical reaction? And the plus sign means and. A and B react together. Now at the head of the arrow, see the head of the arrow? Whatever you have there are the product or products, if you have more than one. And I'll put an S in bracket because you could have C plus D or whatever. You can make more than one product. So you should know, big time no, if I have a chemical equation which shows a chemical reaction at the base of the arrow, the beginning, you have the reactants. At the head of the arrow, the pointy part, I like that. Does that sound scientific? The pointy part. Anyways, at the head of the arrow, you should know you have the product or products. That's a chemical equation. Which shows the chemical reaction in this case, when you combine A and B together, mix them together, it will react, have a chemical reaction to make C. Again, you should know A and B at the base of the arrow are the reactants. At the head of the arrow are the products. Now, when you do write a chemical equation, there's a certain convention. you have to write the correct formulas. The starting materials, notice I have it even here, are always written on the left. These are the reactants. And here, the correct formula of the products, that's what you're making, are on the right side of the arrow of the equation. And if, let's say A was water, you don't write it like this. That's not the right chemical formula for water. It's H2O if A were water. So that's what we mean by the correct formulas. I'll teach you later on, students like to change things to have the incorrect formulas. And guess what? I mark it wrong because it is. Now, continuing on. The reactant and products are separated by an arrow. And they are. And the arrow always is pointing to the products. See, the arrow is pointing to C, the products. Now, plus signs are used to separate different reactants. Whoops. I accidentally touched one of the macro buttons on my writing pad. I've never done that before. All right. Plus sign are used to separate different reactants or products. So if I had something a little different, E plus F plus G makes H plus I. Think of those plus signs meaning and this chemical equation for the chemical reaction, if I react E and F and G together, I will make H and I. Remember, at the base of the arrow are the reactants. And at the head of the arrow are the products. And this you should know. If I were to ask in that chemical equation, what are the reactants of that chemical equation or reaction? And that answer would be E, F, and G. If I were to ask, what are the products of that chemical equation or that chemical reaction? And the answer would be H and I. The reactants are always at the base of the arrow, the products at the head of the arrow. Now, there's a validity check. For a chemical equation, they must be consistent with the experimental facts. What does that mean? Well, let's go back to this reaction. If you go into the lab and mix A and B together, and you identify the substance that is made, the product, it better be C. Otherwise, this chemical equation is nonsense. And that's an important part of a chemical equation for a chemical reaction. You have to be consistent with the experimental facts. And this is very important. because of the law conservation of mass, in a chemical reaction, you never create or destroy atoms. In a chemical reaction, you never create or destroy atoms. And what does that mean? That means there must be the same number of atoms of each kind of element on both sides of the equation, the arrow. And I should also say the same number and same type. And how do you make sure that happens? We have a balanced chemical equation. Now, what is that? And I'll never ask you on a test, what is a balanced chemical equation? But this is important. A balanced chemical equation has the same number of atoms of each element involved in the reaction on each side of the equation. And I'll show you what this means. Another way of saying that is atoms of an element are never gained, lost, or changed into atoms of other elements of during a reaction. So whatever you start with, the number and type of atoms, you end up with the same type and number of those atoms of that elements. All you're really doing is changing things. Think of like shuffling a deck of cards to get something different. And that's what happens in a chemical equation, which shows a chemical reaction. Now, in chemistry, we have an important skill, and it is a skill, called balancing a chemical equation. An unbalanced chemical equation, I'll show you this, is brought into balance. I guess I should have balance here, by adding coefficients, and I'll teach you what a coefficient is in a little while, to the equation to adjust the number of reactants and product molecules present. So what does this mean? Well, let's look at a chemical equation. If you take hydrogen gas and oxygen gas, and you have to put a little spark in there, a little energy, you'll make water, H2O. Now, the first thing, which is always going to have to be true, hydrogen gas has the formula H2. Oxygen gas has the formula O2. And water has the formula H2O. Now, the question is this balanced? How do you find that out? Well, in a balanced chemical equation, you have the same number and same type of atoms on both sides of the arrow. So let's find out. Well, on this side, we have two hydrogens. On this side, we also have two oxygen, O2, two oxygen atoms. Now, on the product side, the head of the arrow, the water has two hydrogens, only one oxygen. It needs to have two oxygen or the same number. For a balanced chemical equation, you have to have the same number and same type of atoms on both sides of the arrow. Instant replay. For a balanced chemical equation, you have to have the same number and same type of elements, atoms, on each side of the arrow. This doesn't have that. What do? Well, we balance it. Oops, that's not what I wanted. So if we have one here and we have two oxygen here, I need to get two oxygen here. Why don't? Well, I can't change the chemical formula. Students like to put a 2 there, and this is a different molecule. That's not water. This is called hydrogen peroxide. You know it as bleach, or one type of bleach. And that's definitely not water. So if you can't do that, how can you get two oxygens on both sides? You change what's called the coefficient, the number in front of the molecule. This is called the coefficient. I always spell it wrong. Hold on, I'm gonna cheat. Dr. White was always the first one down. Oh, I did have it right the first time. I'm gonna cheat big time. I know how to spell it. Don't tell anybody Dr. White's an awful speller. You change the coefficient. And if we need two oxygens on each side, in water, there's only one, I'll put the number 2. So 2 times 1 is 2 oxygens. I changed the coefficient, but now how many hydrogens do we have on the left, on the right? Let me on the head of the arrow. 2 times 2, we have 4 hydrogens. But on this side, we only have 2, and we need 4 hydrogens. How do we do that? You change the coefficient. Well, if this has 2 hydrogens and I need 4, 2 into 4, 2. And now let's check. I'm going to rewrite it so it looks nicer. And now, just like balancing your checkbook, to make sure you balance the chemical equation, how many hydrogens on the left side, the reactants? 2 times 2 is 4 hydrogens. How many oxygens are on the reactant? 2 times 1. Remember, when there's no number in front, the coefficient is the number 1. We just don't write it. So there are 2 oxygen. On the product side, the head of the arrow, how many hydrogens? Well, in water, there are 2, but we have 2 molecules. So 2 times 2 is 4 hydrogen. How many oxygen? Well, in water, there's 1, but the coefficient is 2. 2 times 1 is 2 oxygen. And now let's check and see if we balanced it. And we have 4 hydrogen. We have 4 hydrogen on each side. It's balanced, the hydrogen. We have 2 oxygen. We have 2 oxygen. And because both are the same on both sides, hydrogen, oxygen, we have, yay, a balanced chemical equation. So when you react hydrogen and oxygen together to form water, you need 2 molecules of hydrogen to react with 1 molecule of oxygen to make 2 molecules of water. And that's how you balance a chemical equation. Now, I said, you should know how to balance chemical equations. I have practice problems for that. We're not going to do them yet, because I still have more things to teach you about balancing chemical equations. If I look at the clock, we're just about out of time. And I will tell you this. First of all, I don't know if I mentioned it. When I make a promise to myself, as far as I know, my whole life, I have never broken a promise to myself. I don't break promises to other people too, but I know 100% I have never, ever broken a promise to myself. And right now, I'm going to promise to myself on test 2, there'll either be 3 or 4 where you have to balance a chemical equation. There'll be 3 points each. So on test 2, not test 1 you're doing today, but next test, there'll be either 9 or 12 points out of 100 how to balance chemical equation. And that's something you should practice. And I'm trying to see, is there good YouTube on this? No, I can't find one. I'll let you go to YouTube and look up reaction of hydrogen and oxygen, and you'll see it makes water. In a glass container, they put 2 gases in with a little spark, and boom, it's exciting. And you'll see water form. And when that happens, you should remember the balanced chemical equation. 2 hydrogens, 1 oxygen makes 2 waters. And that's because it's balanced. And the number in front is called the coefficient. You can't change the formula when you balance a chemical equation. And students always want to do that. It's wrong. Trust me, it's wrong. But you can change how many, the number, by changing the number in front, the coefficient. If I look at today's clock, I'm going to end up a whole minute or 2 early. Don't tell anybody. Actually, I don't even have to do videos like this, but I want you to do good in my class. All right, important thing. Don't forget, lab was due yesterday. If you get it in today, I won't tell anybody. Don't forget, you should have included a selfie. I guess you don't do this. You go click of you with some chemicals or equipment from that lab. All right, in a couple minutes, I will be sending out the password for test number 1. You will get it in your email. The password is always lowercase. I like the special effects, lowercase. And you'll take that, and with that password, you'll be able to download the PDF file for test number 1. Boy, this is thirsty work. And you'll take it, and then you'll upload your answers by tomorrow, 1 p.m. for test number 1. If you don't have a printer on a piece of paper, write your answers. You don't have with the numbers and put your name on that. You don't have to write the questions, and you'll take and convert that to PDF file. I have instructions how to do that, and you'll upload it. By this Sunday, 1 p.m. or earlier, I hope a lot earlier, I will have the points you got on test number 1 in Blackboard. By that same time, Sunday, 1 p.m., I guarantee it. I promise myself it. Even if I have to stay up all night Saturday, which I don't, I haven't done before then, but I guarantee by Sunday I will. I will send out an individual email with the points you receive for each answer on test number 1. Next Monday, I will go through all of test number 1 and how you get the answers, the correct answers. I will cut that out of video. How do you like these special effects? I'm ambidextrous. But anyways, I will cut that out of video and make it into a separate video. This is the part with the answers that I go through on Monday. And I'll post that as a private video on YouTube. And I'll send out sometimes Monday or Tuesday morning the URL to access that private video. So if you can't make it to my class, you can still see how to do the right answers. Don't forget, tonight from 6 to 7:15, I have my office hour. And with that, unless you come by tonight and say hello, I'll say have a nice rest of the week and weekend. I'll see you on Monday. Gang gesund. Goodbye. I stole that from Granny of the Beverly Hillbillies. Bye now.